Hi guys! Today I'm going to be talking to you about alcohols, but more specifically the acid and base properties of alcohols. So first off, let's just look at what an alcohol is. Alcohols are a carbon compound with at least one hydroxyl or OH group bound to them. Alcohols can be primary, secondary, or tertiary, depending on the classification of the carbon they are attached to. This carbon is bonded to only one other carbon. The hydroxyl group bonded to it results in a primary alcohol, such as ethanol, which is found in our drinking alcohols. And when the carbon is bonded to two other carbons and a hydroxyl group, we get a secondary alcohol, such as isopropanol, commonly found in rubbing alcohol or hand sanitizer. Finally, if a carbon with a hydroxyl group is bonded to three other carbons, we get a tertiary alcohol like tert-butanol, found in paint removers. There's one other type of alcohols known as phenols, which are a benzene ring with an attached hydroxyl group. These kinds of alcohols are found in plastics and drugs like aspirin. Based on the condition of a reaction you're using them in, alcohols can act as an acid or a base. But before we get into that, we'll quickly review the definition of an acid and a base. There are a few different definitions for acids and bases, including those set forth by Arrhenius and Lewis, but when talking about alcohols, the best definition was described by Bronsted and Lowry. Bronsted-Lowry acids are any species that can donate a proton, typically in the form of a hydrogen ion. Bronsted-Lowry bases are any species that can accept a proton, also usually a hydrogen ion. When we react acids and bases together, the protonated base is called a conjugate acid, and the deprotonated acid is called a conjugate base. Just like all other acids, alcohols that behave as acids have a Ka value, or an acid dissociation constant. The Ka value is a measure of how strong an acid is in a solution. However, typically we look at a pKa value, which is equal to the negative common logarithm of the Ka value of the acid. In terms of acidity, the smaller the pKa, the stronger the acid is. The acidity of an alcohol is based on three main factors: electronegativity, size, and resonance structures. In order to assess these factors, we must first look at the conjugate base of whatever alcohol we want to learn more about. When assessing electronegativity, the more electronegative the atom carrying the negative charge is, the more stable the conjugate base is, and thus the stronger the acid is. We can see below the electronegativity trends from the periodic table. When assessing size, the larger the atom carrying the negative charge, the more stable the conjugate base is, and thus the stronger the acid is. We can see the trends for size on the periodic table as well. Finally, when we look at resonance structures, the more resonance the atom carrying the negative charge has, the stronger the conjugate base, which once again results in a stronger acid. When creating reactions that involve acids and bases, it is important to understand which way the equilibrium will lie. If we mix two reactants, but the reaction favors the formation of those reactants, we won't make any of the desired product. In order to determine equilibrium of these reactions, we can perform a back-of-the-envelope calculation to see which side of the equation is favored by the reaction. In order to do one of these calculations, we need to find the estimated pKa of the starting acid, which is the alcohol, and the estimated pKa of the conjugate acid, which is the resulting alcohol. We take the pKa of the starting acid and subtract it from the pKa of the conjugate acid. We place the result as an exponent on 10 to determine how much the reaction favors the products. If the products are favored by 10 to a positive value, equilibrium will lie towards the products. These kinds of reactions are the most favorable acid-base reactions of alcohols, in which we take a strong acid and base and react them to produce a weaker acid and base than the ones we started with. If the products are favored by 10 to a negative value, equilibrium will lie towards the reactants. This is a very unfavorable acid-base reaction of alcohols, in which we take a weak acid and base and react them to produce a stronger acid and base than the ones we started with. So, alcohols have many different uses within the world, and their ability to act as Bronsted-Lowry acids and bases in organic chemistry just scratches the surface of that.